Were you able to see the screen?
Yes, sir.
Okay, good. So just a brief overview, since we have come across a long distance of theory of generalization, that we have started with the fact that we want to make out of sample error to be zero. In that case, we did it in two ways. One, we make our in sample error zero by our learning algorithms. Second, we want to track how the in sample behavior is tracking the out of sample. So you can see these two equations together is actually meaning that if my E in is close to zero and I say my learning algorithm, I build it in such a way that E in is almost zero, then my theory of generalization will generalize such kind of a less error as well in the out of sample, and we get a generalized out of sample behavior as well. And then we later bounded this whole thing that any bad thing, that is E in, will not track E out by a huge margin, that is epsilon. E in and E out difference is more than epsilon. That means E in is not properly tracking E out, and we make a bound with respect to the growth function, where our growth function is nothing but order of n to the power k minus 1, which is order of n to the power bc dimension. And as we had a little bit of discussion on the VC dimension as well, we compute VC dimension in such a way. And in case of arbitrary d-dimensional perceptron, we have seen, for example, let us take an example of a d-dimensional perceptron. We have seen that in case of that, our DVC is d plus 1, and we proved that. How do we prove it? If you remember that we prove it in two ways. First, we say that any number of d plus 1 points and their dichotomies can be shuttered. So at least d plus 1 it should be. And we have shown at d plus 2 points, we get a contradiction by showing that d plus 2 points, any possible levelings of d plus 2 points cannot be made. Hence, DVC is d plus 1. I can shatter at most d plus 1 points. So with that, we try to deduce the generalization bound in this way, that we consider this to be our delta. So it means what? That the bad thing should be bounded by a delta. In other words, we could see that with probability or confidence more than 1 minus delta, I can find my error less than equal to delta, because I just did a flip of this. Probability of this less than equal to delta is nothing but 1 minus probability of this. That means this sign gets greater than equal to. So with probability confidence greater than 1 minus delta, I will get my error bound to be less than equal to epsilon. And we say that this is nothing but a concept of probably approximately correct learning. And when we do that, from this equation, we configure that from the equation of this delta with respect to MHN and all, we find out that our epsilon is nothing but root of 8 by n ln. Then what it was? 4 mh2n by delta, right? So which means this is actually, so this is the generalization bound. Why? Because see, now here we are making that E out we do not know. We know E in, but we are saying that E out will be bounded by E in with these factors. E in plus this generalization, I am bound to get my E out value less than that. So this is the maximum error that I will make. Yeah, trying to mute whoever is not muted. So this is the maximum error that my learning algorithm, after I learn and minimize my EN, is bound to track my E out within this range. That's it. So that is probably approximately correct. So why it is probably? Because it is a probability bound with a confidence of 1 minus delta. I am sure that with more than 1 minus delta, I am accurately can learn. It is approximately correct because it's less than delta. This is the correctness, approximate correctness of it. So this we call it as something called a generalization bound. We generalize with respect to E out in this bound. Always remember, E out is not in your hand or in your vicinity. You have E in, you minimized it. According to this analysis, theoretical analysis, you find out that I could reach to E out at most with this much tolerance. That is what we finished up in the earlier class by calling it as a generalization bound. Okay. And we also have seen some nuisance about those things, that we need at least the number of samples to be more than 10 DVC by theory, not theoretical, by some practical, by some practical experience we found out. So all these things, the number of BC dimension, you need to at least have 10 times more points in order to characterize. So this is all with respect to the theory of generalization that we did. Let us proceed a little bit also by thinking that what do we mean when we try to approximate a function f? So let us try to introduce the concept of approximation versus generalization. I will tell you the difference between these two. You are trying to learn a function f, unknown. You are only learning it by the eyes of x1 and its level, supervised learning, n number of such points and their levels. So you are not given access to this function. However, you are only given access to the training examples in your hand. Therefore, there is a question. So how do you are picking up something to be correct of this? So something we call it as an hypothesis set H, which contains several hypotheses, H1, H2, and so on. And then my learning algorithm just picks up some G belongs to this hypothesis set. And my theory of generalization say I could generalize this very well. This approximates F very well. Now there are two aspects. See, one aspect is how good is your hypothesis set, because you are asking for a function from this set, nothing else from this set. The second thing is that, so the good your set of hypothesis is, the close you will get to this function, right? So therefore, if you have, so the consideration is, let's say case 1, I have more general hypothesis set, which will imply that more general means I can do many things, and therefore I have higher chances or better chances of approximating the function f. I hope you agree this point. If it is more general,
Yes,
there
sir.
are more possibilities, so you have a better chance to be coming close to it. The second case is the case of finding it. See, there are two parts. One is my hypothesis set is great. That is case 1. That if I could pick up a good hypothesis from there, then I will land up near to it. The second thing, the alarming thing is that you have to search inside the hypothesis through the eyes of your training examples, right? So if this set be more and more complicated, then searching and finding out a better approximated thing may be harder. So instead, if we have a less general hypothesis set, then I have a better chance of generalizing it, because if this set is shallow, if this set is small, then finding the best element from this set is much easier. The best element from this set is what? The best element from this set is that element which tracks the out of sample better. That is the best G, right? So finding best G is much easier in a less general hypothesis set. For example, the interval set is much less general than the set of, let's say, linear combinations of anything infinite. So as you can see, I mean, the ideal would be, I mean, so the ideal is that if your hypothesis only contains F, that is the ideal. You can easily understand. But I just pick up this, isn't it? That is the ideal. Go and buy a lottery. So two concepts are merged when I try to reason about approximation versus generalization. It is the fact that not only the power of hypothesis set matters in the trade-off, it is also the fact that how you exploit over the search space of the hypothesis set and extract an hypothesis which is good. So hence, this leads to us to an interesting point that how well H approximates F. That means how well my hypothesis set contains F or contains certain hypotheses which are much closer to F that can approximate. The second question that we ponder, that how can we find the best among everything is there in H, right? These are essentially the two questions that we are doing. One is the question from case 2, the other is the question from case 1. Agreed or not?
Agreed, sir.
So if you now try to again, I mean, remember that decision list, I mean, the decision trees, concept learning. What do we see in concept learning and decision trees? That if that hypothesis is not contained in H, the version space will be empty, right? And we give a name to that. What do we give a name? Inductive bias. Remember? We give a name that the bias of the hypothesis space is that it may not contain F at all. Hence, the first thing we gradually see, it's a bias, versus the second thing today we will discuss is called the variance, and it's a trade-off between the bias and the variance to determine that how good our learning can generalize. Because it is not only the case that in a hypothesis set which is infinite definitely have the possibility of containing F, but it is also the case that you have to find it, and you have to find it looking from the data points. There is no other reference. The distribution of the data point could be so skewed that you get a very high variance, that you may not at all get the best H. I will show you an example. Let me first complete the theory and then I will show you exactly an example where it happens. Get me? So this is what we will try to cover in today's lecture. Any questions with this intuition that we're trying to pitch in?
No, sir.
So if the
Yeah.
distribution, you were saying, if the distribution is very, if the distribution variance is really very high, it means it is really variated. So we will get the high variance, and we won't be able to find the best edge.
Yes. So what impact it will get, theoretically I will prove, and then practically I will show over an example in details. Nice. Is it a good deal? Just wait for some time. Okay. Urvasi may be annoyed that I started asking a question, you say wait for some time.
Okay, sir.
Okay, good. Let us wait. Okay. So first of all, that small steps I will try to build the theory. We are trying to see E out of G. We will take squared error first of all to make the analysis simpler and try to understand. So for real value targets, just as like linear regression, we will take squared error. So what does E out of an hypothesis G means? Theoretically, it means that a point X, how far it is from X, Fx, this is the error in the for the point only for the one point X. Agreed? Absolutely, there is nothing much to worry about here. However, now here comes the ramifications of distribution, that this is the G that you find out from your learning algorithm given a training dataset from the dataset D. If I have given as another dataset D dash, you could have find a different hypothesis as answer. So I need to just make that indication with respect to some alpha numerals that this is from a D dataset I converge into G, because as you know, as I will also tackle that how good I converge and how good it is from F. Agreed with this equation? Finally,
Yeah.
finally, it's since I done it for one point, it's just an expectation over all the points in the out of sample space, as we did. You know that E out we calculated it using this way earlier also. Okay.
So can
That's
you
how it's
repeat
my.
the concept of D over there? Like why we are
So
writing it?
I
What
give
is
you
D?
a training example. Your learning algorithm gives me the answer hypothesis G. If I give you another set of training example, you give me another G. For the
Okay.
perceptron, let's say, if I give you a training example, your weight be something. If I give you another training example, your neural network back propagation will give you different sets of weights. So that is a
Okay.
different G. So that means I need to somehow maintain this G, because my concern is that how best we can find it within a set and how that approximates the F, both things. So within a set means I started off with a training set. I need to find out for that training set where my G goes. That's why I need to have a alphanumeric notation for that.
Okay, sir.
Okay. You are absolutely pitch on. So ultimately, since we want to also have a generalized notion of this bias and variance, so we will try to make this expectation also going over D as well. I hope this makes you more happy, right? That's what we want. Because now I have nullified the impact of G, because it's an expected value with respect to all the data sets we have, which basically in a continuous space you can integrate in a different space. You can just do a summation and then an average. Agreed?
So for different data sets, right?
Yeah,
For a
for
lot of
different
data
data sets
sets,
I can get different G, so I just get an expectation of the E out over the data sets. That is my actual E out that I want to see. Okay. So now just for the mathematical jugglery, look at these terms. Since the inside term is a square term, it's a positive term. So therefore, I can turn this in a reverse way also, because it's a positive term. It doesn't matter the way I write it. People will statistics will be agreeing to me. Otherwise, if you just see the expectation equations, you can easily see it's an integration of fx into dx, right? What is expectation of x? Just try to find out what is expectation x of fx. It is an integration from a limit low to high fx dx, right? If this term is positive, the way you take x and d, you can just flip it, na, integration side wise. If you're not convinced, just open a statistics book. This is a very first nomenclature that they do. Expectations, if the term is positive, you can flip it. So let us try to focus on inside aspect first. Later we will come this EX. First, let us decompose this one. So to evaluate this thing, we define something called an average hypothesis. What does that mean? That means that I have a hypothesis set. Let's say M of them. And I want to make sure that in this hypothesis set, where is the average or the mean hypothesis resides, which means that the average hypothesis would be look like this. It's nothing but it will be the same as it will be expected over the distribution. What does it mean? See, your learning algorithm gives a particular G with respect to the distribution that I gave. So I can give a different distribution, you can get a different hypothesis, another G dash, another G double dash by a third distribution, by a fourth distribution, another G triple dash. So where is the mean? I mean, with respect to all expected value of G, I can find with respect to all expectation with respect to the distribution that I am given. If I take the expectation of them, that will be my average hypothesis. This is the definition that I make. So in other words, let us imagine you have distribution D1 up to dk. Then obviously your G bar X, suppose you have this K discrete distribution, is obviously is an average of K equal to 1 to K. Any dk you take and make a hypothesis. This is what do we mean by the average hypothesis. And which in statistical parlance, because this distribution is drawn from a sample and made a distribution, so we need to make expectations. This average doesn't work out in generic way. Agreed?
Yes, sir.
This is how we define it. Now this inside part, let me try to write that inside part. What I am doing is I'm just extracting the inside part and rewriting it in this way. Just I'm doing an arithmetic jugglery to explain the notion of bias and variance. So when you do that, this will be with respect to D. I just minus and plus it, nothing else. Same equation is still there. Now this will be square, A square plus B square plus 2AB I will do. Nothing. This is my A and this is my B. I taken A square plus B square plus 2A into B. Now look at this expectation over this, the cross terms. What does it mean? This is a constant because this is over D. This is also a constant because there is nothing D involved here. So since these two are constant, so what does expectation of D this means? It means that I need to only take the expectation of this into 2 into, that is a constant. So this I need to make into 2 into G bar X minus Fx. That's a constant term because see integration Fx dx, if this is a constant, you know what happens. Okay. So what does this mean? Expectation of this one, look at the formula here. What does this mean? This is again, this does not have D inside it. Only this has D inside it. This means G bar X. This remains the same. Doesn't it cancel the cross term altogether? Yes or no?
Yes.
It cancels the cross terms altogether. So we have this and this. Just remember what we have. I am rewriting once again. We started off with this. And we found out. Sorry. And we found out that it is of two terms. One is this minus G bar X square. I mean, sorry, this does not P anymore. This one C. I mean, here there is D. Sorry, the next term there will not be D. This one plus agree. This is what we get because this term has D inside it. We need to keep it. This term is devoid of any D. We just separate it out. Yes or no? I mean, the calculations, you can do it yourself and get the same thing.
Yes, sir.
Yes, sir.
So now see, now again, let us reiterate this. How well H approximates F, meaning the average hypothesis that can be possible by H is my best hypothesis because it's a cumulative way of thinking that which is the best possibility out of here. How it is getting close to this. The second thing, that any hypothesis you pick up, how it is close to your average one. We are doing it in two steps. You pick up by finding your own hypothesis, looking at the data, how close it is to the average or the best one from this set, and how the best one from this set is approximate or is closer to F. So now I think you can easily understand that this is your bias for X and this is your variance of X, right?
Yes, sir.
So therefore, where we started off doing this over this over E out, right? This is where we started off with E out of GD. And then we just swapped it and tried the inside part it. So this thing still remains. This thing still remains with it. So which is nothing but this right, and we finally we call it as a variance plus bias. So you can see the expected value out of sample, sorry, you can see that the expected value out of sample of this, the error in the out of sample obviously will be dependent not only on the bias but also on the variance, which gives us to a very interesting point that if I sufficiently make my hypothesis spread generic, then my bias will reduce because the best hypothesis will fit in the F very closely, but then there is a chance of increasing my variance. Pictorially, Suppose this is your f function and this is your hypothesis set H. So therefore, your best hypothesis could be here somewhere. And this is the distance from the best hypothesis. I call it as a bias. On the other hand, suppose I have a very generic hypothesis set. There are so many points in the hypothesis space I can choose from. My f sits here. Let me color it another way. My f sits here. This is my f. Therefore, you can see that the variance is with respect to all these distributed points. Let's say my gx is very close here. I mean, it's a very well popular set, and my g bar x is very close. My bias is very low. However, you can see if looking all these elements inside the set, I have to find a g. So the variance with respect to gx is too much. So any good g I find out by searching here is widely, maybe in wide distance with g bar x. So therefore, the efficacy of the algorithm with respect to hypothesis set, if you complicate the hypothesis set, you can easily see if you complicate the hypothesis set, obviously your bias will be reduced because your f now will be contained inside it. So your best hypothesis can connect it easily. Whereas the alarming situation is that variance will be very high because you need to search through and get a point here. You are searching by looking at the training example, nothing else. That may be of a larger distance than G. So, with respect to the model complexity, sometimes the learning estimation also there is a trade-off, which we call as a bias versus variance trade-off. That's the theoretical part. I will immediately follow it up with a detailed problem. Any questions with the theoretical layout? Okay.
Yes, sir.
Good. Now let me start with the definition of doing this. So let me start that. Let's say my example is sign target. I give you an example that my function unknown is from -1 to 1 is the domain, and the range is a real number where I want to learn the function of x, which is basically sine of pi x. You do not know it. You only look in terms of the data points that you are given. But the irony is that I will give you only two training examples. I will give you only two training examples. And let's say I have two hypotheses to compare that whose bias and variance are how much. So one hypothesis, I take it as, let's say hx is a constant. And the other hypothesis, I take it as, let me just color it in another color because it will be easy then. Hx is a line. So all the hypotheses that are of constant nature. So it means that your hx is a constant, means it's a line which is parallel to the x-axis, and it's a general line. That's what my two hypothesis power is. And obviously you can understand that the power of this is much more because h1 is a superset of h0, because when your a is equal to 0, then h1 is obviously h0. Get it, right? The power of h1 is definitely more than the power of h0, right? So
Yes,
these
sir.
are the given hypothesis to test my bias versus variance factor.
So the function you took, it should map to the -1 to 1, no?
Yeah, it should
That you
map to the
wrote.
-1 so that I could draw now. I mean, see, I am
So
doing
how you
the,
wrote -1 to 1, it is mapping to R. That is also fine, but
Yeah, because x, if you put -1 to 1, it's a real range. So between pi to plus pi to minus pi, sine of that, it's a number. I'm drawing the function for you. No worry, I'm just drawing the function for you. So this is my zero line. Let me put my zero line somewhere here to look good. So therefore the function could be like this. Oh, sorry. Mistake. Right? Sine function.
yes, sir.
So
I'm
there.
saying the above example you took, like you were mapping it from -1 to 1
Mhm,
to R to
mhm.
R.
R is a real
But
number.
sine, yeah, R is a real number, but sine will give us between -1 to 1. No?
Yes, yes. Pi to plus pi to minus pi. Na. It will only be -1 to 1. Na.
Yeah.
Oh, you are saying this one. I mean, yeah, I mean, sine will give you from 0 to 1. I mean, not 0, -1 to 1. So you can just range it.
Yes.
You can just range it, no
Okay.
issue.
Okay.
That's it. No, that is not a problem. So with H0, that the blue hypothesis. So as you can see, the best fit could be this, right? I mean, the best fit. I mean, if I could get at this hypothesis, this is the best which we can do, isn't it? I mean, what else you could do with a line which is being parallel to my x-axis? You cannot do anything. So there you can understand the error that hypothesis H0 will make in the out of sample case is the area that I draw here, right? And it, we experimented it also. I mean, it just comes if you compute the probability distributions and all, it just comes like this. Totally acceptable because it's a 50% of the thing that I am making right. Whereas if you go for H1, so again, I need to draw the line here. This will be very interesting. Just look at a little bit afterwards when we introduce my bias and variance. So here you can see with the best fit could be somewhere here, right? I mean, if we could fit in the line like this, right? Because that is the point when I can minimize the whole lot of error, because here my error will be this, this, right, and maybe this one. Agreed. That's how we get the error.
Yes, sir.
This is the ideal scenario. I mean, if we could fit in this way, I do it in this manner. However, you do not know this line because you are not given with the function. Instead, what you are given is very alarming. 2 points. Let's say that I am given with these 2 points in this manner. Let's say the points are like this. One point is, let's say it is here. The other point is here. So you can easily assume that it just comes down, goes up, again comes down and gets these 2 points. So for the sake of completeness, let me just draw it once again. This is not known to you. You only look these 2 points and try to fit a line. So obviously your blue hypothesis will try to fit a line somewhere in between these two. So assuming that, let's say this point is a little bit up, try to fit a line somewhere in between these two. Agreed? Because that minimizes my error most. Yes or no?
So we are finding the. So we are try to fit between these 2 points only, right?
You are finding
That's
this
why that.
particular from this hypothesis set. You are trying to find the find the value of b by only looking at these 2 points. That's what you do in learning, right? I give you 2 points. I give you a hypothesis set. Fit it
Okay, okay, sir. Agree.
here. The same thing. if you go with this, let me just draw again the mysterious curve that we do not have in our hand. Only we have this point and at this point. So the best way, this is a little bit more, functional. So I will try to fit a line which minimizes the error maybe in this manner, passing through these 2 points. Only 2 points I can pass a line through this. Agreed?
Yes, sir.
So therefore, you expect that here, by looking at this, it is this much. You expect that the error becomes like this. Everyone is with me, like, I am only seeing Urvasi is saying yes. Others, all are with me, right?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir.
Okay, good. So the thing is that, see, probably that if we have this kind of a factor, that these 2 points, maybe we are seeing the number of regions that I shaded by orange. Maybe this is better. However, these are 2 points, and now let's come the distribution D data point factor coming in. Let us put that in. Then what will happen is exactly this figure. So here the gray lines that you can see, these lines are dependent on how much data points you are given where and where. So it will be exactly in the middle line if the data points are typically in the both end of this spectrum equally balanced. It is the topmost gray line if the points are biased towards there. You get it? So these are all the answers of the hypothesis that I get from different distributions of D's. All these lines. Okay, this one is just for
Yes, sir.
hypothesis 0, which is B. Hypothesis 0 set, which says that my Hx is equal to B. Oh, I just dropped it somehow. Just give me a second. Let's save first. Oh, thanks. Okay, so where I was here, right? These are different things that can be possible by different distributions of D given to me. I can get this line, I can get somewhere here, I can get somewhere here. And as you can see, the gray region is more darker in the middle because this is symmetric. So 2 points randomly taken would maintain this symmetry to a much extent. Okay. Whereas, so now the question is that this is my average hypothesis, because all these gray lines that I get, the spectrum of grays, I try to figure out which is the mean portion of it. I get this one, right? This is the average
Yes, sir.
hypothesis that I can get. And this is somehow, this portion indicates the variance, because you are now trying to figure out among the possible hypothesis set where I should lay down and choose something. That is your variance, right? In your hypothesis, you are searching it. You will be alarmed to see the case for H1, where my Hx was Ax plus B. See here, if my point is 2 points, I want to fit it with a line. So this will be the line decoration. I hope it is easily understandable why this decoration comes this way. Right?
Yes, sir. Yes, sir. Yes, sir.
So
Yes,
among
sir.
them, the denser
Right.
thing is whatever we fitted in the best kind of that. It may not be the best line that we started to fit in like this here, but because it depends on the data distribution of the random data set points that we give. So somewhat like that. It will be somewhat like that. Now you see the alarming point here, this one. Look at the variance. That means with this range of variance, I need to search for this best line. I'm giving you the ballpark figure now. Here, if you do a computer analysis of it, here the bias will be just like this, which is more or less understandable because maybe the data distribution made it like this. The variance is 0.25. Here the bias is earlier the best line was 0.20. When I analyze it with random points, it came as 0.21. Not that bad, but it's okay. It depends on which points I give. Do you know what the variance came here? An utter disaster. Which means that it is indeed, so you are trying to make E out as small as possible. Randomly distributed data sets are given to you. Two choices of hypothesis are given to you, which means if you are only given 2 points to answer with, this wins by a large margin because my bias plus variance is the expected outcome of E out is 0.75. Here my bias plus variance is 1.9. What does it signify? It signifies that though if you find a good hypothesis that is much closer in case of an arbitrary line with respect to the function that I am trying to find out, but finding that is much more difficult. Agreed with this point? Is any everybody?
So the bias is average distance. Like here you took to 0.50, so
Bias,
it is
so
on
so
an
the bias is,
average.
see, bias is among the data points that are given to you. You took all the lines and you took the mean of this line, that is g bar x. Your bias is nothing but this g bar x, how far it is from the actual function, and we take a squared error for that. And then we get an expectation with respect to the d values. Here, if you see the with respect to x values, here if you see this where your bias is this with respect to x we do it. Okay, so those who do not know machine learning, you go and tell me that we learned from our teacher that sine function, if we try to fit in constant is the best, not a line. I mean, other people may think you mad, but you know what you are making sense of. Anyway, so this is the point that I am trying to make, is that it's not about the fact that how expressive your hypothesis is. You have to do well in out of sample. It is also the fact that how you choose from that such a vast expressive hypothesis and choose a best candidate. If your hypothesis is very good, but you cannot choose the best among them, you are similarly bad in the final estimation. Then your hypothesis is restricted, but you can choose always the best there. Get this analogy, what I am trying to make here?
Yes, sir.
Yes, sir.
That's what
Yes,
bias
sir.
and variance is all about. And that's why I told that day that when somebody asked about what is the bias and variance, he could not understand. Then I told him that just wait for a minute because there is a lot more things to discuss here. And that's what we mean. Okay. So in terms of the learning curves with respect to simple model, that is the simple hypothesis set that we want to fit in, and the complex hypothesis set where we do go, let us see that and end our discussion for today. Suppose my model is a simple model. If my model is a simple model, just think in mind that I have H0 given to me, the simple one. So therefore, whatever good you do, your expected error would be very high. Isn't it? I mean, see, whatever good you do, you can best fit here, your expected error is a much higher than a model which is much more succinct. Right? So there you see the E in that you are trying to minimize with respect to the sample error will go like this. Let me try to 29. Yeah. And the E out that you are trying to do, since I am squared error, it looks like symmetry, will come in like this. So for a simple model, if we see that this is how I do my E out and how I go with my E in, and this is the expected error. You cannot, I mean, the actual expected error. So this direction I put my error. You cannot make it better because this deviations will always remain in terms of the error because your model is simple. It's just a constant line. Whereas if I go for a complex model, your expected error is much lesser because my model can now fit very well and can approximate the function very well. So my expected error is very less. So here this is a complex model. Model means complex hypothesis set I am giving to choose from. My model is also, that's why complex. Then what will happen to E in is the same way. See, E in will look like this. Why? Because this is the number of data points in x direction in both sides. When there are small number of data points, the number of data point is small, E in will be 0 because E in perfectly fits them. Suppose you have only 3 data points. I give you a fourth order polynomial to fit in. You can easily fit in with a fourth order polynomial all the points. So that's why initially it will be 0. When it crosses the complexity of the model, the order of the model, then it starts to rise. And A out, if you go by this, it will be wavered like this. Initially, what will happen, you see, when you are only fitting exact data, it is kind of infinite. Why? Because you are memorizing, you are not learning here. It's absolutely bad in terms of generalization. You're just memorizing and trying to fit the curve like this. You are, this is a point, 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 you are trying to fit it. Whereas all these points is nothing but a straight line. So therefore, if you look closely into this phenomena or the curve that I have drawn, you will get an analogy of BC analysis, and that is the generalization and in sample error with respect to bias and variance. So what that will look is as follows. That let me suppose this was my expected error. I was coming with E in like this, and I was coming with my expected error like this. So you can see that your in sample error is this much at any given n. This is your in sample error, E in, right? Your generalization error, I can easily understand at any point your generalization error is this much because this is your omega. Understand? Because E out minus E in less than equal to omega. So this is my generalization error. Pictorially. Now let us also look at the same bias and variance analysis for the same curve. Our expected error was here. We started off with the in sample error, something like this. We started off the generalization error, something like this. So this is our E out. This is our E in. Now, can you tell me what is the bias and what is the variance here? What was our bias? If this is the expected error, which means the error that make by the average hypothesis. So isn't it this is my bias? And isn't it this is, yeah, tell me.
Bias is nothing but is error, right? Like with that G, with that
Yeah,
formula,
because
expectation of G bar.
exactly we have, see what does, just let me write the bias formula. What does bias mean? Bias is g of x minus fx square, because I assume that squared error is my assumption. So my bias looks like this. So it is effectively at the error between your expected value of the hypothesis chosen and the correct one. It is this part.
Yeah. Yeah. So there is
What
like
is your variance? Yeah, is your variance is this part, because variance is nothing but what is g bar x with respect to the gx that you have chosen. The gx that you have chosen will produce this one, E out of G. Agreed? Yes or no?
Yes, sir.
Hence,
No, sir.
hence, E out of G is less than equal to E in of G plus sigma that we consider for the generalization bound. Here, the same thing reveals that E out of G is less than equal to E in of G. I mean, I'm not saying E in of G, it's a bias plus variance. Okay.
Yes, sir.
Just try out the example. I just leave it to you. Just try out with the example of a linear regression. Example of linear regression to find the bias and variance. The only assumption you can make is that the best approximation error in linear regression, let's say it is sigma square, kind of a standard deviation. And try to do all these analyses by yourself that I have made with respect to the formulas. Okay. You'll be amazed to see also
Yes, sir.
that, as I said, these are the part of my point where my E in is 0 is basically the VC dimension. From the point that it gets raised up is VC dimension plus 1. And this you will find out from the linear regression. I just, not everything I will do it for you. Just try to think in this manner. Okay. So a small summary, since
Yes,
we are
sir.
already over with the time. So a small summary. We started off with the theory of generalization, and we thought that it is a good thing that to combine both, I will do it with this picture, that how good we can reach from our hypothesis to F, and how good is to search within this and find the best hypothesis. So that is, the first one is the bias. So this one is the bias, and this one is the variance. And indeed, we find out that the expected out value of a hypothesis that you get out by looking it to only given training points is just by bias plus variance, which is also a generalization boundary with respect to in sample. And we have seen that there is a point, if the age goes up, then my bias goes down, but my variance can go up. And that's why the sample model that we come up with the complex sample model, we get these features with that. And we have seen a practical examples where we do that, and it's disaster in case of if we try to fit it a general line, because finding a general line position in a sign graph is more difficult than just resting with only a simple line, because finding it is so easy, maybe that makes a higher bias, but the total thing is drastically reduced. With that notion, we also tries to make a interrelation between the generalization and approximation with the bias and variance, which is basically approximation part is bias and the generalization part is variance. In fact, in case of linear regression, since this curves is symmetric, 2 into variance is just the generalization error if the curve be symmetric. That's it. So thank you. That's all for today. And if you have any quick questions, I can answer. Otherwise, we are out of extending our time.
So I have a question.
Yeah. Yeah.
So,
Yes, please, sir.
so can we say that the model having a high variance is overfitting in the model having the higher bias is underfitting?
Tomorrow's lecture. I'm coming. Good queries. I mean, all these are rational queries as we proceed. And I'm happy that you are having these rational queries because it's just a follow. Tomorrow's lecture will be on the overfitting.
Okay, sir. Sir, I have another doubt. What is this lecture regarding the assignment 2? Can I ask it now?
As, I mean, in the project assignment, you're saying?
Yes, sir.
It is better if you could mail me with a CC to the TA, or maybe mail TA with a CC to me. It would be good.
Oh, okay, sir. I have mailed to the TS. I will also send it to you.
No,
please?
they will answer. Just give them 1 2 time. They will answer, and I'll check. I will check with them.
Okay, sir.
Okay, thank you. So I'm stopping my recording.